Hi everybody. This is the lecture on section 5.1, integrals of two variable functions over rectangular domains, or regions, I guess. So recall the definition of the integral of a single variable function. Okay, you're really going to have to keep in mind what the definition of an integral here is in this class. In previous classes, often students confuse the fundamental theorem of calculus for the definition of an integral. That's the fundamental theorem of calculus, which is a consequence of the definition of derivative and of integral. So here, in order to really understand what's going on, we need to keep in mind, really what the definition is. And the definition is as follows, right? So you have a function, f of x, continuous function, on a interval, and you cut up the interval into subintervals, x1, x2, x3, x4, and then you take the function to make these rectangles, right, to govern the height of these rectangles here. Right, I'm using right-hand endpoints. Of course, you can use right hand or left hand or whatever the case might be. Whatever's your favorite. Doesn't affect the outcome. So the area between the curve and the x-axis, right? So here delta x is equal to b minus a over n. Xi is a plus I delta x. And the integral from a to b of fx dx is equal to the limit as n goes to infinity, the sum I equals 1 to n, fxi delta x. Right, this is the area of these rectangles, which estimates the area between the function f of x and the x-axis. And then the estimate gets better as n tends towards infinity. So the definition of the integral is that, right? The limit as n goes to infinity of these sums called Riemann sums, right? So we're going to use this definition of an integral to measure various other things, aside from the area between f of x and the x-axis. In Calc 2, you use this to do various other tasks, calculating work, calculating volumes, and things of that sort. So here in Calc 3, we're really going to expand on that and do some real nice stuff. Measure some really interesting things with the notion of an integral. Okay, so now consider a continuous two-variable function z equal to fxy over a rectangular region. R equal to, we'll say a less than or equal to x less than or equal to b, c less than or equal to y less than or equal to d. So in the xy plane, we're looking at this interval, not interval, but this rectangle here draw. Okay, so we've got this rectangular region, and what we're aiming to do right now is to measure. So let's define an integral which measures the volume of the solid underneath, well, between the surface z equal to f x y and the xy plane. So the picture looks like this. So you've got this rectangular region here, and above that rectangular region, above that rectangular region, or below, right? But I'm just going to draw above, just to simplify the look of the thing. You get, some sort of surface given by this function, z equal to fxy. So here's some sort of example here. And it gives you that surface there. And we want to measure the volume of this solid here. And then regions below the xy plane are considered to be negative volumes. Regions above the xy plane are considered to be positive volumes. So regions above xy plane are considered to be positive volume, and regions below the xy plane are considered to be negative volumes. Okay, so we're measuring these volumes, and normally, like, we just draw stuff within the first octant here. It would be more confusing to try to draw it below, so we keep the drawing simple. So this thing that I've drawn here would be a purely positive volume. Okay. So how do we estimate it? Well, we estimate in the same way that we do, well, not in the same way, in an analogous way that we do with single variable functions. Okay, so define the double integral as follows. So first we need to define a Riemann sum. So let delta x equal to b minus a over n, and delta y equal to d minus c over m. Xi equals a plus I delta x, and yi is equal to c plus, well, let's say j. Yj is equal to c plus j delta y. So once you do that, you take this rectangle here and you subdivide it into smaller rectangles. Actually, this is probably not the best illustration for that, but we'll try to make it work. Let's see. So we've got this rectangle, right, and we'll say that the subdivisions for x, there's 4 of them, right? So you've got x1, x2, x3, and b is x4, and then we'll say there's just one. Y1 and Y2 is for D. And now this subdivides this rectangle into subrectangles. Right? And at each corner in the subrectangle, right, this is the point Y1, X1. Maybe we should use a different color. So this is the point Y1, X1. This is the point Y2, or no, not Y1, X1, X1, Y1, X2, Y1, X3, Y1, X4, Y1, X1, Y2, X2, Y2, X3, Y2, X4, Y4. So that's where these points, or what these points are. And I'm going to use upper right-hand points. Doesn't matter which point you use within the rectangle, but you take those as sample points. Now, the volume of the following box consider the following box. So we're going to take the box whose upper right hand corner is x, I, y, j. And then the height is going to be f, x, I, y, j. And then we're just going to block it off. Right, this is the point x, I, y, j, 0. And this is the point x, I, y, j, f, x, I, y, j. So the volume of this box here is the area of the base, right, times the height. So the height is f, x, I, y, j. And the length and width are delta x, delta y. Right, so this volume is f, x, I, y, j, delta a, where delta a equals delta x, delta y. Right, so delta A is the area of these rectangles here. So each subrectangle has area delta A equal to delta x, delta y. Delta x is the distance between the x's, and delta y is the distance between the y's. All right, so those boxes, the volumes of all those boxes together, they would estimate the volume of this solid here. So we've got these boxes underneath this guy here. So the sum of the volumes of these boxes estimates the volume of the solid. All right, and that estimate is what? It's a double sum. The I equals 1 to n, the sum of the I equals 1 to n, and the sum over j equals 1 to m, f, x, I, y, j, delta, a. So we write it as a double sum. It's the sum over two different indices. The sum I equals 1 to n, j equals 1 to m. Right, so the sum over all these points here. Right, I goes from 1 to 4, j goes from 1 to 2. So it's the sum of the volumes of those boxes. And then the estimate gets better as delta y and delta x go to 0. Gets better and better as delta x and delta y both go to 0. Okay, so the desired volume is exactly the limit, okay, as delta y and delta x go to 0. In other words, as delta a goes to 0, of the sum I equals 1 to n, the sum j equals 1 to m, f, x, I, y, j, delta a. Okay, and this, we just call it the double integral. The double integral of fxy over the rectangle R. The notation is as follows. Is, well, we use two integral symbols. What does the integral symbol mean? Right? It's a long skinny s. Right? Right, the S stands for sum. It's a skinny sum because those rectangles or those boxes are getting very skinny. So instead of being one sum, like the single variable integral, right, instead of being one sum, like the single variable integral right here, we have to have two sums, one for each variable. Right, so we're using a double sum, so we use two s's. So it's the double integral over the rectangle R, f, x, y, and then we use this thing here for the differential, dA. And that's equal to this thing here, this sum, Riemann's limit of Riemann sums. So that's the definition of the double integral. Okay, that's the definition. How do we calculate it? Right? This doesn't tell us how to calculate it. I mean, we never really calculate integrals. I mean, you can calculate integrals directly from this, but it required those weird formulas, if you remember those weird formulas, right? The sum I equals 1 to n of like I squared is n times n plus 1 times 2n plus 1 over 6. You know, it required this kind of thing, these weird summations. And all you could really calculate were the integrals of polynomials and exponential functions. using that. I don't know if your Calc 1 teacher went over it. He or she should have, but maybe they didn't. But we don't really calculate integrals using that. You can estimate integrals using Riemann sums. As far as getting exact answers go, we don't do that. We use the fundamental theorem of calculus, that the integral of a function is the difference of the antiderivative at b and at a. Right? The integral from a to b of f prime x dx is equal to f of b minus f of a. That's the fundamental theorem of calculus. Well, we can adapt that to this case. We don't actually need a new fundamental theorem for double integrals. We just adapt this one to this scenario using a technique from Calc 2. So how do we calculate this? Okay, we use iteration. So for iteration, it looks like this. So recall from Calc 2 that if you've got a solid that's lined up along some axis, okay, the solid doesn't have to be, particularly circular or round, right? But you've got some solid lined up on an axis, say on a t-axis. So here's t equal to a, here's t equal to b. That's a t-axis. And then at t itself, the cross-section of this solid, right, has area a of t, some function of t. Right, so the cross-sectional area perpendicular to the t-axis has area a of t. In which case, the volume of the solid is what? The volume of this solid is just the integral from a to b of the area function, a of t dt. Okay? So we can apply that to this situation. Okay, let's go back to that picture of that solid volume that we are trying to calculate. So we apply this idea as follows. Okay, so here on the x-axis, we're going from A to B. We're going from A to B on the x-axis. And then at a given value of x, you've got this cross-section here. So for a fixed value of x, you've got this cross-section. So the cross-section at x has area equal to, well, what is it? All right, this is y equal to d, and y equal to a is back there. Or y equal to c is back there. Has area, well, x is fixed, right? X is held constant, and now we just integrate the function for y. As area, the integral from c to d, f x y dy where x is considered to be a constant. Right? So x is considered to be a constant, so this is just a function in terms of y. So we can integrate a function in terms of y using the fundamental theorem of calculus with respect to variable y. So doing an antiderivative in terms of y, a partial antiderivative, if you will, and then evaluating at c and d. Therefore, the volume the total volume is, well, it's the integral from a to b of the area dx. And what is the area? Let's do it a little bigger. All right, it's the integral from a to b of the cross-sectional area, dx. Well, what's the cross-sectional area? It's the integral from c to d of f x y dy. So when you calculate this inner integral in terms of y, it leaves you with that constant x. So that's a function of x. And then you integrate that function of x from a to b, and then you get a number, a plain number. So this is just denoted by the integral from a to b, integral c to d. So we call this an iterated integral, f x y. Now you don't write dA here. You write dy dx to signify that you're going to calculate with respect to y first, and then x second. So we do the integral with respect to y first on the inside, and then we do the integral with respect to x second on the outside. Okay, and then this is called an iterated integral. Okay, and then one very interesting consequence is that the iterated integral can be calculated in two different ways. With the answer guaranteed to be the same for each. Right? That is the double integral over the rectangle R of f x y dA. So that's the abstract notion of the double integral, is equal to this iterated integral that we just talked about from c to d and then a to b of f x y dy dx. But you don't have to do y first and then x. I mean, you know, in this picture, right, we did the cross-sectional area at x, but you do the cross-sectional area at y and integrate with respect to x first and then y. It's the same picture, same idea. There's nothing sacred about x coming before y, because we're using alphabetical order. So it's also the iterated integral from a to b and then c to d of f x y dx dy. So let's do a nice example that shows you know, how we calculate this in two different ways. Oh, by the way, this is called Fubini's theorem. All right. So let's calculate the double integral 6 minus xy dA over R, where, example, where r is equal to the rectangle x goes from 0 to 2 and y goes from 0 to 3 in two different ways. Okay, so the first way, the double integral over r, 6 minus xy dA, is equal to, so first let's integrate x and then y. 6 minus xy dx dy. Okay, so first we do an antiderivative with respect to x, where y is considered to be a constant. Okay, we're doing the integral with respect to x, where y is considered to be constant. So we take the antiderivative with regard to variable x. Right, so instead of a partial derivative, it's a partial antiderivative. Right, so what's the antiderivative with respect to x? Here, it's 6x minus 1/2 x squared y. And that is evaluated from x equals 0 to x equals 2 dy. Right, the antiderivative with respect to x, 6x minus 1/2 x squared y, y is a constant. And now we evaluate that from 0 to 2. Evaluating from 0 to 2, okay, so I'm going to evaluate each term separately. So this is 12 minus 0, so I just get 12. And then this one is 4 times a half, which is 2y minus 0. So that's 12 minus 2y dy. So all the x's are gone, and I'm left with a function of y. Right? No x's, just y's. So now we do an antiderivative with regard to y is 12y minus y squared from 0 to 3, which is equal to 36 minus 9 is 27. Okay? The other way around, 6 minus xy dA is equal to the iterated integral from 0 to 3, 0 to 2, 6 minus xy dy dx. So that's the integral from 0 to 2. First we do the antiderivative with regard to y. 6y minus 1/2 xy squared, evaluated from y equals 0 to y equals 3, and then dx. So, evaluating at 3, what do we get? We get 18 minus, 18. 18 minus 9/2 x dx. And at this point, there's no y's, just a function of x. All right, and now the antiderivative with regard to y is, or with regard to x, is 18x minus 9/4 x squared from 0 to 2. And this is equal to 36 minus 9 times 9, 81 over 4, or that's a 2. 2 times, 4 times 9, or it's just 9, 36. Right, this is 4 times 9/4 is 9. So 36 minus 9, 27. All right, so same answer. as it should be. Not as it should, as it must be. So that's a nice way to kind of check yourself sometimes, is to do the integral twice and see that you got the same answer. If you got different answers, something went wrong somewhere. All right, so there's plenty of examples that we can do, but I'll just leave it to the discussion during class, where we'll do a bunch of examples together. So that's the end of the lecture on this section.